Welcome back, everybody, to another day of Math 210 Calculus. It's great to see you. And so today, if you're following along in the book, we're going to be looking at section 3.3. And so this is about like what we call like the product and quotient rule. So it teaches us how to take the derivative of a product of two functions. It teaches us how to take the derivative of a quotient of two functions. So there is a little bit of theory in that I can explain, like why the product rule and quotient rule are true, but mostly this class is all about calculating. So how to calculate derivatives, and get a result. So like all of calculus isn't like that, but this particular section is. So I'll try to focus on examples for the most part. I'll go through some of the explanations a little bit if we have time. I do have a 2-video series on this that I posted online beforehand, and I'll teach this class as if you've watched those, but it's just 15 minutes, so definitely check it out if you haven't got a chance yet. So what I want to first do is introduce what are the product and quotient rules and how do you use them, and I'll start with product rule. Actually, even before that, I'll start with a brief review, because last time we learned about it has been a little while, so last time we learned about the power rule, which says that if you take a function like f of x equals x to the n, where n is any real number at all, then its derivative f prime of x is going to be equal to n times x to the n minus 1. We saw special examples of this. We saw the derivative of x squared was equal to 2x, x like n equal to 2 there. So then the derivative is 2 times x to the 1 is equal to x. We've seen, did we even calculate like x cubed and show that was 3x squared? I don't know if we did that or not. We certainly we could do that. But a generalization of those things that we know is that for general x to the n, the result is n times x to the n minus 1. In order to formally prove this, you need to use Isaac Newton's version of the binomial theorem. It's a super cool proof, but I think I'm not going to prove every single thing in this class. That's more like an analysis class. And here I'm just more interested in having given you a couple of examples and then showing you the general rule that's based upon it. For product rule, let's get into that. So say that you've got the product of two functions. So you've got function f of x, you've got function g of x, and then their product is f of x times g of x. And so you're interested in taking the derivative of that product. Is there a way that you can rewrite it in terms of the product of the two derivatives? Let in a few more students. Is there a way that you can rewrite that in terms of the product of like the derivatives of the functions? And your first guess might be that you might hope that this is equal to f prime of x times g prime of x. I think it's pretty reasonable to hope that. Unfortunately, this turns out to not be true. So I can give you some examples that show why that isn't true. So for example, if you look at f of x equals x, g of x equals x, then f of x times g of x is equal to x squared. And the derivative of x squared, we know, because we've calculated it, we also know it from the power rule, but the derivative of x squared is equal to 2x. But on the other hand, f prime times g prime would be the derivative of x times the derivative of x. Derivative of x is 1 because of the power rule, or because f of x equals x is a linear function with slope 1. Its derivative is equal to 1. So the product of the derivatives in this case would be equal to 1, whereas the derivative of the product is actually equal to 2x. So it can't be true that the derivative of f times g is equal to f prime times g prime. So what is it? I'll give you the formula now, and then I'll show you where it comes from, like a little bit later on. But I'll just leave it for you to ponder. But I will show you maybe like a little bit, though. Because if you want to know what is the derivative of f of x times g of x, like if you go back to the definition, that's how you would do this. You would have to go back to the definition, which is limit as h goes to 0 of, and the function is f times g, so it's f of x plus h, g of x plus h minus f of x times g of x. Right? Think of this as like a new function called h of x, and like, or like maybe called like k of x, and k of x plus h would be f of x plus h times g of x plus h, minus k of x would be f of x times g of x. You're dividing by h. So this will maybe show you why it can't be true that this is the product of derivatives, because while it is true that there is the product of limit law, that is to say that the product of two limits is the limit of the product, this, you can look at it and see pretty clearly that this is really not going to be the product of the difference quotient for f by itself times the difference quotient for g by itself. If it were, then you'd expect to see like an h squared on the bottom. You'd expect to see something a little different on top. So it's, when you actually write down the definition, you start to see that there's really no hope that derivative of f times derivative, the derivative of f times g could be f prime times g prime. But I will show you how to work with this and get the right answer a little bit later on. So what is the right answer? What is the actual formula for how to write the derivative of f times g in terms of the individual functions? It's going to be f prime of x times g of x plus f of x times g prime of x. So this is what's called the product rule. This is what's called the product rule. I need a board that's like twice as big because I have all this information I want to keep on it. But I want to give you some examples too. So the hypothesis or the assumption is that f of x and g of x are differentiable functions. Their derivatives exist at every point x. And then the product of the two will be differentiable, and this will be a formula that gives you the result. Let's see it in action. So first, there are things that you can calculate in multiple ways. So if I take f of x equals x, g of x equals x, then f times g is going to be, like, yeah, let's use this example we talked about before, that f times g would be x squared. And then I know that its derivative is going to be 2 times x. But let's figure it out using the product rule. Product rule says first take the derivative of f, which is 1, multiply it by g of x, which in this case is x. So 1 times x is x. And then add to that f of x, which is x, multiplied by the derivative of g of x, which is equal to 1. So what you get is x plus x equals 2x. So the power rule and the product rule will give you the same answer. Which is kind of nice. Any question on that? Let's do a bunch more examples. So let's do a book example. So let's take f of x equals x squared and g of x equals 9 plus x. So let's do, so therefore the product is equal to x squared times 9 plus x. And your assignment is to find out what's the derivative of f times g. And there's 2 ways to do this. And I'll show both ways. So one is to use the product rule. The other way, you could just multiply this out and use the power rule on each term. But first things first. So let's do the product rule first. So that's going to be derivative of f, which is derivative of x squared is 2x, times g. G is 9 plus x. And we add to it f of x, which is x squared, times the derivative of g of x, which is equal to 1. Well, how did I know that so quickly? Well, for one thing, 9 plus x is a linear function with slope 1. We've seen that whenever you have a linear function, like a function of the form y equals mx plus b, then the slope of that linear function is going to be the derivative. You could also say derivative of a constant is 0, and then add to that derivative of x, which is 1. And you know, breaking it up into 2 terms, you could see that the derivative is equal to 1. So finishing up the algebra here, it looks like the derivative is 2x times 9 plus x squared. I mean, we can simplify this a little bit, I guess. So this is 18x plus 2x squared plus x squared. 18x plus 3x squared. Unless I made a mistake there, check me for mistakes and put it in the chat. I'm not always going to have my eye on the computer, but if you put something in the chat, I'll see it within a minute or two. I try to check in. So that's one way you could do it. Another way you can take this derivative is to expand out f times g first. And by the way, like when you're just doing derivatives, the way the problem will be presented to you is it'll say, like, take the derivative of this function. So it'll be up to you to identify what you want to choose for f and what you want to choose for g. But since you've got 2 things multiplied together, it makes sense to choose f of x equals x squared, g of x equals 9 plus x. But okay, so what's another way you can calculate this derivative? So I would multiply through and say, this is equal to 9 times x squared plus x cubed. This is equal to 9 times x squared plus x cubed. And what we learned last time is that basically because of the limit laws, derivatives are what we call linear. You can break it up term by term. You can pull out the constant. So I can calculate this derivative by first looking at the derivative of 9 times x squared and then adding to it the derivative of x cubed. And how can I calculate the derivative of 9 times x squared? Well, that's going to be 9 times the derivative of x squared. So that's going to be 9 times 2x. That's what I mean when I say pulling out the constant. So that's part of what we call linearity, the derivative being linear, meaning you can break it up over a summation. You can pull out the constant. That's like my comment last night. Like, you couldn't do this with sine of x. Like, it's not true that sine of 9 times x is 9 times sine of x, because sine is a nonlinear function. But derivatives themselves are linear, so derivative of 9 times x squared is equal to 9 times derivative of x squared. Then you use that power rule to make x squared as 2x. So putting it all together, you would get 18 times x, and then plus the derivative of x cubed, which is 3 times x squared. Ending up with 18x plus 3 times x squared. So it's kind of nice that you get the same answer no matter which way you choose to calculate. There's no one way that's better than any other. Choose to calculate any way that you want. You can see this as the product of two functions and use the product rule, or you can expand it out and then differentiate term by term using the power rule in this case to get the same answer. So any questions or comments on that? I went ahead and erased it. I'll bring it back later on. Let's look at another book example. So let's please take the derivative of t squared times e to the t. And so it makes sense to use the product rule here. You have to choose what you want your function f of x to be. You have to choose what you want your function g of x to be. But there's natural choices here since you've got t squared times e to the t, so I think I'll choose f of x equals t squared g of x equals e to the t. Their product is therefore t squared times e to the t. So what's the derivative of that product? So following the rule f prime times g, that's the derivative of t squared, that's 2t, times g, that's e to the t. Remember, e to the t is this exponential function with the base being this number e, which is like which is like what, like 2.71 or something like that. It's an irrational number. Sorry, got something in my throat. Apologize for that. You don't want to hear me coughing all the time. I don't want to cough all the time either, but it just happens when you're talking a lot. Yeah, so e to the t is this exponential function. We'll talk more about what the number e is later on in the class, but it has this unique property that its derivative is equal to itself. E to the t can be uniquely characterized as the smooth function who's equal to its own derivative, and also gives you the number 1 when you plug in 0. So this is f prime times g, and then it's plus f, which is t squared times g prime, and derivative of e to the t is e to the t. So then you can collect your terms, and you're just going to get 2t plus t squared times e to the t as your answer there. what does it mean? It means that if you graphed this function t squared e to the t, and you plug in any particular point, then the slope of the tangent line to this function at whatever point you plug in would be given by this formula. Which is another kind of cool way of thinking about it. Let us do one more example. Oh yeah, so here's one that's kind of cool. So let us do x to the 5th. And take the derivative. And you can do this multiple ways. The easiest way to do this is not with the product rule. In fact, it's not immediately clear how you can do this with the product rule just by looking at it in that form. The easiest way to do this is to rewrite x to the 5th over x to the 4th as being equal to just x. And then you see its derivative is equal to 1. So like, I don't want to confuse you or something. Like, it's definitely true that x to the 5th over x to the 4th is equal to x, and therefore its derivative is equal to 1. But I want to illustrate how you can get this answer another way using the product rule. So there's another way you can rewrite this. This is basically an advertisement for algebra working, no matter how you do it. So you can rewrite this as x to the 5th times x to the minus 4th. So 1 over x to the 4th is equal to x to the minus 4th. And by exponent laws, when you add these exponents straight across, you'll still get x as the result. So that's consistent with what we've said before. But let's take the derivative of this with the product rule. So we're using f of x equal to x to the 5th, g of x equal to x to the minus 4th. So this, we're being a little bit silly, yeah, that's fine, but we're trying to illustrate that the product rule works no matter what, and compare it to use something to calculate an answer, even when we already know the answer. So this is going to be, we can use the power rule each time to help us. So this is going to be derivative of f times g. So derivative of x to the 5th is 5x to the 4th times g of x, that's x to the negative 4th, plus f of x, x to the 5th times g prime of x. And g prime would be the derivative of this, and now you apply the power rule to it. So that's going to be negative 4 times x to the negative 4 minus 1. So it's negative 4x to the minus 5. So this is the answer, but of course you'll want to simplify it. I definitely hope that you'll simplify all of your answers and not leave them like this, because this is really hard to read, right? What's easier to read, this or just writing down x? So like that's why we want to simplify our answers. So let's do simplify this. So x to the 4th times x to the negative 4th, that's x to the 0, which is equal to 1, so that's just 5. And here we have negative 4 multiplied by x to the 5th times x to the minus 5th. Again, add those exponents, get x to the 0, which is equal to 1. So you end up with 5 minus 4 equals 1. So yes, that's a really convoluted way of recovering the fact that the derivative of x is equal to 1. But it shows that all of these rules are correct. It shows that You can use the power rule and the product rule, or you can do algebra first. No matter what you do, so long as all your steps are correct, you'll eventually land on that answer. Which I think is so neat and maybe a little bit underappreciated, how it's not just that calculus is like a collection of rules, it's that all of these rules, they have to be part of a bigger tapestry, and they have to be able to interact with each other in such a way that that you always get the same answer no matter how you apply the rules. And if you think about it in that way, this formula is the only way that all the rules could play nice together and be correct. So like after you get more perspective, you begin to realize that this product rule is actually really natural, and you know, trying to hope for f prime times g prime would actually mess a lot of things up. Any questions or comments on any of that? Okay. So I will take a little bit of time to try and show what's going on here with like the proof of the product rule, but I'll try not to spend an outsized amount of time. Like I'm not trying to give you a formal proof, but I'm just trying to explain like why this really makes sense. And we've seen that the definition of derivative of the product of the two functions is limit so h goes to 0 of what? Well, you take the function, you plug in x plus h, then you subtract f of x times g of x, and then you divide through by h. And so there's this, so what I'm doing is the explanation that's in the book. You can also look at it too. So there's like a geometric way to understand this numerator. The numerator is f of x plus h times g of x plus h minus like f of x times g of x. So it's not a, it's not super formal, but it's really useful. So if you think about a rectangle where, let's say, like, think about this as representing f of x, and you think about the full length as representing f of x plus h. Yeah, so like maybe you had f of x, and f of x plus h was a little bit bigger. On the other side would be g of x plus h, and maybe like this, just this little part, or like maybe this first part here would be, you know, g of x. And so same way on the other side too. So like this length would be g of x, the entire length would be g of x plus h. So then geometrically in this picture, what does the numerator represent? F of x plus h times g of x plus h is the entire rectangle. It's everything. But then you're subtracting away f of x times g of x. And so what is left is this shaded area, right? So the shaded area, that's the part in the numerator. And the question is, can I rewrite the shaded area in such a way, can I rewrite that numerator in such a way that it's going to make the problem simpler? And so this is how we'll break it up. So we'll look at it as this piece, and we'll look at it as that piece. So like maybe I'll call them like 1 and 2. So the numerator is equal to 1 plus 2. And so what's the formula for the area of 1, I guess that formula is, well, this length is f of x plus h, and right, that's this horizontal length, and I guess the vertical length is what? What's that vertical length? It's just this little piece, right? So it's g of x plus h minus g of x. Like, do you agree with me? That's just base times height. That's the area of this top sort of strip. It's this base times the height, which would be g of x plus h minus g of x. And then I'm going to add to it this number 2. And so what's that? That's going to be, again, base times height. So the height in this case is just g of x. And the base is going to be this length here, which is now f of x plus h minus f of x. And what I'm saying is that this is equal to the numerator. So this is equal to that. They say the proof is in the pudding. In this case, the proof is in the picture. And it's also true just by algebra. If you multiply this out, you'll get a cancellation. You'll see it's equal to that. But the reasoning for why they're equal just comes from the geometry here. The numerator is the shaded area. Put that shaded area into 2 pieces, and it's those two things. So what you're wanting to do, actually, you don't really need to put a box around it because I want to work with it. So what you're wanting to do is to take the limit as h goes to 0 of all of this divided by h, which, the limit of everything divided by h. And of course, with fractions, I could split it up over a common denominator and make it this plus that. And now you're seeing, like I hope, what's going to happen, which is using that product limit law, right? Let's rewrite this first term as f of x plus h times g of x plus h minus g of x over h. That's how fractions work, right? Think of this as like f of x plus h over 1 and multiply straight across, and you had what you had before. So the limit law says that I can calculate this as limit of f of x plus h as h goes to 0, which is just going to be f of x, times limit as h goes to 0 of this difference quotient, which is nothing but the definition of g prime of x. Similarly, the sum limit law says it's going to be this plus that limit, and I can pull out the g of x, taking the limit as h goes to 0. Limit as h goes to 0 of this is f prime of x, which is exactly what you get down here in the product rule. I mean, it's this term corresponds to that one, and this term corresponds to that one, of course, but that's how you prove it. So it's not f prime times g prime, because it's not like there's 2 difference quotients being multiplied together. No, what happens instead is that there's 2 difference quotients being added together with these extra factors involved. So that's how the product rule works. Let me pause and check any questions. Oh yeah, there's a question on one of the previous examples I did. Maybe we could talk after class. But yeah, so that's the product rule. So last chance for questions before we erase. And there's a rather nice explanation of this in the textbook as well in section 3.3. So I promised we should also talk about the quotient rule. And so here it is. So quotient rule tells you how to take the derivative of a quotient of two functions. So in this case, you've got two differentiable functions, f of x and g of x. And you're taking the quotient f of x over g of x. And you're asking yourself, how do you take the derivative of the quotient of two functions that you know are differentiable, and you know how to take the derivative of them individually? And once again, like, I'm just going to tell you the formula and then practice with it a couple times, and then I'll briefly show you how to derive it. So here's the formula. It's f prime of x times g of x minus f of x times g prime of x divided by g of x squared. It's a little harder to remember than the other one. Yeah, it's a little harder to remember than the other one. There's no good way to remember this. I mean, there's some sort of mnemonics or songs or something. I don't really like doing that myself, so I'm not going to subject you to it. But I just remember you take the derivative of the numerator first. So it's f prime g, then you're subtracting f g prime. And then you're just squaring the denominator. Let's examples. So let's start simple. Let's take f of x equals x, g of x equals x. So these are two differentiable functions. And we know x over x is equal to 1. So we know the derivative should be equal to 0. But let's check it out. X over x prime, so it's going to be derivative of f, that's 1, times g, that's x, minus f, which is x, times the derivative of x, which is 1. Everything divided by x squared. So you can see where this is going. This is just x minus x over x squared, which is 0 as expected. So the quotient rule is performing in a way that we would like. I'll even do, what was the other one that I did? Let's do this one. Let's do x to the 5th over x to the 4th. So f of x equals x to the 5th, g of x equals x to the 4th. We've seen this twice now, because one way you could rewrite it as x, take the derivative, it's going to be equal to 1. The other way, you could rewrite it as x to the 5th times x to the negative 4th, and do the product rule on that. So now let's compute it a third way. So let's just straight up use the quotient rule and see this in action. So this is going to be derivative of f, so derivative of x to the 5th, that's 5 x to the 4th, times g of x, x to the 4th, now minus f of x, which is x to the 4th, times the derivative of g of x, which is...
Isn't it x to the 5th, for like x to the 5th times 4x to the 3rd?
x to the So the f of x times g prime, yeah, so, yeah, thank you. X to the fifth times g prime, which is 4x to the third. Yeah, thank you. Thank you for the correction. And then we divide by g of x squared, which in this case is x to the fourth squared, right? And so, yeah, so there's our answer, but it's not going to feel very good until we kind of reduce everything and try to simplify it. So x to the fourth times x to the fourth, add up those exponents, that's x to the eighth, so I get 5 times x to the eighth. I'm subtracting now, x to the fifth times x to the third, that's x to the eighth, so I get 4 times x to the eighth, and now I'm dividing x to the fourth squared, so when you have an exponent raised to another exponent, you multiply 4 times 2, of course, 8, giving me x to the 8th. So that gives me 5 minus 4 is 1, so that gives me x to the 8 over x to the 8, which is equal to 1. So it does indeed give us the answer that we expect. And of course, you wouldn't want to use the quotient rule on a problem like this. Of course, you'd want to simplify first, realize that you're just taking the derivative of x, and then know that the answer is equal to 1. But this is an example chosen to illustrate that both these rules, are consistent with what we already know. That we really can do this stuff multiple different ways. Let's take another example. Let's calculate the derivative of e to the t over 1 plus e to the t. So like on the next test, one of the problems will be, please calculate the derivative of the following 2 or 3 functions. It'll just be like a list of functions, and you'll just sort of calculate through and show your steps. You'll be using either the quotient rule or the product rule. So you'll see stuff like this. So how do you calculate a derivative of e to the t over 1 plus e to the t? You recognize it's a quotient of 2 functions. So you think, well, the numerator is e to the t. The denominator is 1 plus e to the t. Let's plug in and use this quotient rule. So let's say f prime times g. So e to the t, the derivative of that is still e to the t multiplied by g, 1 plus e to the t minus f, which is again e to the t times g prime. So what's g prime? So you can calculate this term by term. The derivative of 1 is equal to 0. The derivative of e to the t is e to the t. So g prime is just e to the t. And you're dividing everything by 1 plus e to the t squared. And yeah, that's your answer. Can we simplify it? I don't know. It doesn't really look like there's going to be a factor of 1 plus e to the t on both on the numerator. So unless I'm just missing something. So I'll just factor out e to the t here. And I'll do 1 plus e to the t. Ah, yeah, that's nice. So just factoring out e to the t, 1 plus e to the t minus e to the t. And if you'll let me maybe just erase that. So it's going to be 1, which we don't even need to write. So it's just going to be e to the t. That's the numerator. Over 1 plus e to the t squared. So this is our answer. That's kind of a nice simplified form. That's how I'd leave my answer if I were doing that problem on the test. So this is the formula for the quotient rule. Where does it come from? How can we show it? It has to be consistent with the formula for the product rule. So that's the trick. So here's the cool idea for how you can show this. So like if you make a new function, call it q of x, like q for a quotient. It's going to be f of x over g of x. So we want to find the derivative of q of x. So this is going to be, right, the derivative of q of x is equal to that. That's what we want to discover. But here's the thing. So like I want to discover this formula by using the product rule. It turns out that really the product rule and the quotient rule are kind of like the same. They're connected by the following fact. If I multiply both sides of this equation by g, I'm going to get that g of x times q of x equals f of x. And what I can do is I can say, well, okay, let's take the derivative of both sides of this equation. So if it's true that g of x times q of x is equal to f of x, then it must be true that the derivatives are also equal. That is to say, it must be true that the derivative of f of x is equal to the derivative of the product g of x times q of x. And so I can now use the product rule on the left-hand side. So let's go to work. So let's use the product rule on that. So that's going to be g prime times q plus g times q prime of x. And so I do want you to be at the operational level where you've just got these committed to memory, so you can like do things like this. And this is going to be equal to f prime of x, right? So here's the logic so far. I defined my function q of x. I want to find its derivative, multiply both sides by g to get g times q equals f. Therefore, the derivatives must be equal to each other. Calculate the derivative of g times q using the product rule. And I think I can just solve for q prime of x. That's going to be my idea. So I'm going to get g times q prime of x, I'll bring this to the other side, equals f prime of x minus g prime times q of x. But remember, q of x was like f over g. So g prime of x times q of x, which is f of x, over g of x. And let's use that common denominator. So let's do g of x divided by g of x. So now you see all the pieces coming together. So I'll just rewrite this now. Over here, I think, I'll just rewrite that right-hand side as g of x times f prime of x minus g prime of x times f of x all over g of x, just using that common denominator g. And remember, this was equal to g of x times q prime of x. So now just divide both sides by g. Or multiply both sides by 1 over g, if you like. So you get q prime of x equals g of x squared. And so I wrote it slightly differently, but you know, I wrote f prime times g instead of g times f prime. Doesn't make a difference. You can see that this is where the formula comes from. We really get f prime times g minus f times g prime divided by g of x squared. And that's the derivative of q of x. That's the derivative of f over g. So the quotient rule follows immediately from the product rule just by using that little trick. So I think that's really neat. I always enjoyed that when I was in calculus. So yeah, the learning objectives of this class are pretty clear. It's memorize the quotient rule and the product rule. It's be able to do examples of computing derivatives that are products or quotients. It is to be able to derive the quotient rule from the product rule. And it is to have an idea of how that product rule is derived. So that's section 3.3. So any questions or comments? All right, hearing none, have a great day. I'll see you on Wednesday. There is homework up for Friday. It's based on 3.1, 3.2, 3.3. You now have the tools and knowledge to do that homework. I encourage you to like aggressively get started on that. And you've got 2 office hours this week. Monday, that's today, and what is it, Thursday, from 2:30 to 4, and today from 3:30 to 5. So definitely get in touch if you'd like any help on that homework, but go ahead and get to work. And thank you, everybody. Have a great day.
Thank you.